Now, if you critically think, multiplication operation, unlike addition subtraction operation, it involves clock, it involves steps to perform, and that is beyond multiple cycle of the clock. It is not done in one clock cycle. It need to have a multiple clock cycle. The question is there any way we can do it in one clock cycle? Like, mostly the question is there a way we can combine it, or we can use it using, we can design a combinational circuit to perform the multiplication. Okay, if we can do it, then you are kind of avoiding all these clocks and steps and everything. Answer is yes, we can do that. We can design a digital circuit which, like a faster combinational multiplier. What we are trying to do in this circuit is that instead of repeating like partial product, like calculation at each clock cycle, we are kind of loop unrolling the whole thing and deploying like 32, actually 31, if you think of, 31 adder, 32-bit adder, deploying like as a hardware, like we are increasing the hardware element there. And each stage, each partial product stage, if you can think of this paper pencil, each of the row, and we are computing each row the partial product, we are deploying adder for each of this partial product computation. We can do that because algorithm point of view, multiplication is always forward propagating. Like you multiply on one stage, compute is partial product. Then next you multiply next bit, then add up to the partial product, make the next partial product. So it is like kind of always a forward propagating nature, like from top to bottom, if you think of your paper pencil method, right? With that, we can, since it is a forward propagating, we can make use of that observation and make a combinational circuit. So what we'll do, we will like take, let's say, start with the LSB, like replicate 32 times, and with multiplicand, that becomes your product of that step, right? And then your product of the next step. Now by the circuit, like we are basically, what we are trying to do here, from that first stage product, we are picking up, let's call it a S, okay, at that sum, at that product, at that partial product computation step, and we are picking up the LSB of the S as my final result, that is my product bit 0, okay. And then rest of the 31 bit we pair it with a 0, basically 0, and rest of the 31 bit make it a 32 bit, and we are adding it with the next step. Next step is again multiplicand ANDed with your multiplier, like second bit of the multiplier replicated 32 times, and we are adding them. Now with that addition, what we are now doing as special from the previous step is this, okay, common thing we are doing, we are picking up the LSB of the sum, partial sum from this next stage, make it this product 1 bit, and instead of picking up 0, unlike we are doing it on the very first, for the very first step, multiplication step, we are picking up the carry out from the adder and using that to make a 32 bit, right? So it is really not a carry out, it is basically a participation of the next stage addition, right? So that's why we are combining carry out with rest of the 31 bit to make a 32 bit operand for the next place adder, okay. And the next place, next like second adder would be, the other operand would be coming from multiplicand ANDed with third bit of the multiplier 32 times replicated. And then from that second adder, we also take the LSB of the sum as my product 2 bit, and the rest of the 31 bits, it's prepended with the carry out from that adder stage to be the next stage operand for the next adder. So in this fashion, what happens, we deploy like 31 adder, and the very last adder will give me a 30, I would say, yeah, that adder will give me whole 32 bit. Like before that, if you can imagine this is there are 31 adder in that stage, and we last adder is going to give you 32 more bit. Okay, this is becomes your P63 to your P32. Okay, the entire thing. Okay, your 0 to 31 being computed, and then last stage adder is going to give you a your 32 bit, the higher part of the 32 bit. Okay, just to make sure we understand the last this 31st adder, what is coming out of this, right? So see, each stages, right, we are taking out one bit and finalize that as my product bit, right? So adder 1 gives me product 1, adder 2 will give me product 2 bit, adder 3 will give me product 3 bit. That's when the 31st adder will give me product bit 31, right? And then we are out of this adder, we are having 31 more bit, but we need 32. Like that 32nd bit is basically your carry out. So we are combining the carry out and the rest of the 31 bit to make a 32 bit high register position. So this P63 is practically the carry out of the adder from the last addition operation, and that gives you total 64 bit of result.